In today's lesson, the goal is to explore the concept of conjugation, or complex conjugation, as we call it. It's a fairly important topic in the geometrical interpretation of complex numbers, which we want to continue talking about, and it will allow us to unpack some more properties of complex numbers to flesh them out fully. Of course, now that we're dealing with a number system which comes with an imaginary into real part, so I have z equals a plus bi. Obviously, we have two different variables. We have the real part and we have the imaginary part. And we can use algebra to play around a little bit more with it. So that's what we're going to do today. So the main idea here is reflection of the complex number across the real axis. So in the last video, we discussed the notion of taking a complex number. So we have a over here and b over here, and we have a number here z, and this can be represented by the coordinate pair on the imaginary and the real axis. So what we want to consider here is we want to consider the reflection about the x-axis. So if I have this line segment joining the origin to AB, then I can also have this line segment joining the origin to a negative b, okay? So obviously the notion of complex conjugation is fairly simple algebraically, and that is reflected in this definition. So the complex conjugate of the number z equals a plus bi is called the conjugate of z, which is denoted by d bar, defined by the following formula, a minus bi. Of course, we're just changing the sign of the imaginary part to reflect it about the real axis so that it now has a negative imaginary component. So this might seem a bit arbitrary, and you might be wondering why we define this. So it turns out that we have a couple of properties that we can discuss. So here are the algebraic properties of the conjugate. So if I want to take the complex conjugate of the sum or difference of two complex numbers, I can simply take the sum or difference of the conjugates themselves and then add them together or subtract them. There's only an addition sign there. There should be a minus sign under there as well. Anyways, if I would like to take the product of two conjugates, or the conjugate of a product, I can take the product of the conjugates. If I want to take the conjugate of a quotient, I can take the quotient of the two conjugate numbers. And finally, there's another way we can define this as well, in terms of the real and imaginary parts of the complex numbers. I find these definitions to be slightly arcane, but nevertheless we'll go through them. So the real part of z is equal to z plus its conjugate over 2, and the imaginary part is equal to z minus its conjugate over 2i. Okay, so hopefully that makes sense. Anyways, the most important definition comes from the definition of the square of a complex number. So z squared is equal to z times its conjugate, okay? So this would be important in quantum mechanics. In quantum mechanics, you deal with wave functions in which the wave function itself is a complex number or a complex valued function. So that would present a problem because the purpose of quantum mechanics is to perform observations on different types of particles and their velocities and momenta and positions. So you can't really do that if you're dealing with a complex wave function that you need to evaluate. So what you do is you square it. So you take the wave function times its conjugate function, and then you have what you call the norm squared of the function. And with the norm squared, you can actually do things with it because it will give you a real function from which you can take measurements. So that was a brief aside, I suppose. We can perform an example now. So this one is Seth and Snyder exercise 1.2.3. So for this one, we need to examine the solutions to the quadratic polynomial. We want to show that if z is a solution, then so is z bar as well. Okay, anyways, let's look at this now. So if we can have this little formula here, what we want to do is we want to use the quadratic formula. So the general polynomial that we're going to do is z squared plus coefficient a sub 1 times z plus another coefficient a sub 2. And that's equal to 0. Okay, so that's how we can solve a polynomial for its zeros. Now, of course, we have the quadratic formula, such that, sorry, that shouldn't be a, that should be z. Z is equal to negative a sub 1 plus or minus the square root of a sub 1 squared minus 4a sub 2, all over 2. And note that we don't have a quadratic coefficient in front of the second order term. Okay, so if you remember from your algebra classes, we have here what we call the discriminant inside of the square root factor. And this traditionally would tell us whether our equation has 1, 2, or 0 real solutions. So we can look at this at the different cases in a more advanced way. If we have that a sub 1 squared minus 4 times a sub 2 is greater than 0, then we automatically know that our solution is in the real set. However, if it's less than 0, then the solution will look something like this. We factor out the square root of negative 1 outside, and then we get the square root of 4a sub 2 minus a sub 1 squared because we factored out the negative. Now, what's important here is that because the discriminant is negative, we have the I there, and we also have this plus or minus sign here. This means that this is going to be put in the form of a plus or minus I times b. Of course, this yields two solutions, which is a plus ib, which we will call z, and a minus ib, which is equal to z bar. Okay, so by definition here, we can see that we do have indeed two solutions, and it is the complex number itself as well as its conjugate. Okay, so I hope that this brought a little bit of theory into the idea of the complex conjugate just a little bit more. We'll talk about this in the idea of function theory a little bit later on. But before we move on to function theory, we want to consider some more things. So in the next video, we've discussed the rectangular representation of how we can model these points. So we've modeled it with B and A, so B there and A there. But we also I would hope that this would kind of look like a vector, almost like a position vector. But note that we can also model it by the values of theta and the magnitude of z as well. So we'll look at the polar representation as well, and in addition we will explore the idea of the Euler formula, and we'll derive it from Taylor's series, which is a Calculus 2 topic, I believe. Thank you for watching, and we'll see you the next time to talk about the polar representation.